Okay, so the last thing in chapter 3 is what we call computer output. Okay, so there are programs that are used to take statistics, to crunch statistics, to do statistical programs, computer programs. We do not use any of those programs. Okay, so nothing you have to do in this class involves a computer. The most computer thing we use are our calculators, right? But the only thing is you have to be able to read a computer printout. Okay, so there's there's some statistics computer programs um, that kind of do what our calculator does, but when it spits out the data, it looks different than our calculator's data. It's the same data, just looks different. So what I'm going to show you today is just how to read it. Okay, because sometimes what they'll do is they'll give you computer printout, computer output. That means it came from a computer. They didn't use a calculator; they used a computer. We don't have to use a computer, we use a calculator, but you do need to know how to read the stuff because all the information we need is here. We just need to know how to read it. Okay? So this comes from handspan. So handspan is the distance from the tip of your little finger to the tip of your thumb. So if you spread out your fingers as wide as you can and you measured from the tip of your thumb to the tip of your little finger, that's handspan. Okay? That's how you measure your hands. So researchers gathered data in order to predict a person's left hand span using their right hand span. So, based on their left hand span, they tried to predict what their right hand span would be. Okay, that's what they were trying to do. So, the scatter plot of the data has a linear form. Okay, so it's a linear relationship. Okay, we know that. And this is the computer output. So, they give us all the information that we need, it's just kind of hidden. Okay, so the first thing is the linear form. So if we're interpreting R, we would say linear relationship or linear association or linear correlation, right? That's that. Okay. And then the next thing is dependent variable. Dependent variable, okay, is left hand span. The dependent variable is which one, the X or the Y? The Y. The Y is dependent. Independent is X, dependent is Y. So that means Y, the response will be left hand span. That's what they're trying to see if right can predict left. Okay. And then you see right hand span here. Right underneath where it says predictor, that's where the X will be. Okay. Okay, so the first one says the slope. What is the slope? The slope is in here. So think about their equation, right? Think about our equation. When we're writing an equation, let's see, here's an equation right here. It's, well, you know what? Let me write it up here. The generic form. Y hat equals A plus BX, right? That's the generic version. That's the one that's in your calculator, right? When you go calculate A and B, that's the one that's on your calculator that you find, right? Okay, so A is the y-intercept, B is the slope. So they're asking us for the slope. Slope is always attached to what? What is slope always attached to in the equation? X, right? It's always attached to X. That's how we can tell the difference between slope and y-intercept, okay? That's how we can tell the difference. So let's go down to the table. Let's go down to the table. We know the X is here, right? The X is here. So the coefficient, so really, slope is a coefficient of X, right? Slope is a coefficient of X. Coefficient means the number in front of a letter. Slope is a coefficient. So we're going to go down here and we're going to go, here's the X, here's the coefficient. This co-F is coefficient. Where they meet, that's the slope right there. That's the slope right there. That's what our slope is going to be. Okay. Now the y-intercept doesn't have a letter with it. It's by itself, right? It's always by itself. So that guy's coefficient is a constant because it's a constant. So right below where it says right hand span, it says constant. So you look at the constant coefficient, that is the y-intercept. Okay, that is the y-intercept. So that's where you're always going to find the slope and the y-intercept. Okay, so we can use those to write the equation in context, right? Instead of y equals a plus bx, we're going to write in context. Okay, so it starts with y hat. Y hat is predicted, always going to be predicted something. Predicted y. Well, what is y in this case? What did we say y was? Left hand span. So predicted left hand span equals. And then the next thing is always the y-intercept. Well, the y-intercept is 1.4365 plus. The next thing is always the slope. And then the last thing is the x, right? And in this case, we said the x was the right hand span. Okay, so there's your equation right there. So the nice thing with computer output is you don't need a calculator because they give you all the data. The hard part is you got to find it, but it's always going to be in the same spot. So you always know where to look. So it doesn't matter what the computer output looks like, it's always going to be the same spot. When you find, you'll have something called predictor. Sometimes it says predictor, sometimes it doesn't say this, but you'll have one that has something, you'll have one that says constant. If you, this is always, the one that says something is always going to be the x. So then you go meet underneath where it says coefficient, that's going to always be the slope. And then where it says constant is always going to be the y-intercept. Okay, there's a couple other things. You see here, S. S is the standard deviation. So what does that mean? Well, we talked about that yesterday. Right here in yellow. So what that number means is on average, how far are each of the points away from the predicted line? How far are each of the points away from the predicted line? That's what that means. Okay, so that number hey. So on average, it's 0.6386 each of those dots, however many dots there are. It doesn't tell us how many people they asked, but on average, each of those people, probably inches, so are within 0.6386 inches of the predicted line. Okay. The next one's r squared. R squared we talked about. R squared we talked about. It's pretty high R squared. Remember R squared we talked about? That is, it accounts for the variation. So we can say that x accounts for the variation of y. In other words, the explanatory variable is this percent responsible for the response variable. So in this case, we would say, let's see, right is the explanatory, left is the response. So we would say the right hand span is, what was it, 90%, 90.2% responsible for the left hand span. That's what we would say, just like that. Just switch out that word for whatever x is, switch out this word for whatever y is, and then change the percent because the percent will always be different. Okay. R squared adjusted, don't worry about. We don't use that in this class. You don't ever have to worry about r squared adjusted. Sometimes they'll be the same, sometimes they'll be a little bit different. So don't worry about r squared adjusted, just worry about r squared. Okay? All right, so interpret the slope in context. Interpret the slope in context. So we're going to use our sentence frame. From not this set of notes, but the last set of notes. Nope, that's this one. This guy right here. Nope, not that guy. This guy. All right. Interpret the slope for every one explanatory variable, comma, the response variable either increases or decreases by that number. Okay. Y-intercept interpretation. When the explanatory variable is 0, the response variable is whatever the number is. Okay. So for the one we just did, we would say for every one, does it say it says uses inches? I don't want to assume it's inches, so we'll just say 1 unit of explanatory variable. Okay. Explanatory variable, again, for this guy is right hand span. And span, comma. Response variable, which is left hand span. The left hand span. Increases or decreases? Well, our number is positive. Our slope is positive. So we're going to say increases. So what it's saying is for every inch your right hand grows, your left hand's going to grow almost an inch. Right? Because you kind of think it's your body, right? You think if one hand's growing, the other hand's going to grow, right? So we would expect something to be, for every 1 inch I grow my right hand, my left hand should also grow an inch. It's saying it's about there. If we round up a little bit, it'll be there. Okay. Correlation coefficient. What's correlation coefficient? We usually don't call it correlation coefficient. We call it something else. Close. R. It's just R by itself. Okay. So let's go back up to the data. Do they give us R anywhere? There you go. Yeah, we could take the square root of R squared. We don't have R, but it's just the square root, right? So the square root of that number, change it to a decimal point. So change it to 0.902 and then take the square root. 0.9497. Okay. So that's what it is. That's what R is equal to. When we interpret it, we need strength, direction, and linear relationship. Okay. So how strong is that number there? Strong, yeah. It's very strong. Okay, so we would say strong. Is it positive or negative? It's positive, but be careful because this number R squared is always positive because you square it. It's always going to be positive. This number here can be negative as well. Okay, so if you take the square root of this, you're always going to get a positive, but that doesn't necessarily mean this guy's going to stay positive, right? So if I don't, what's another way to tell if this guy's going to be positive or negative? There's another way to tell. The slope, yeah. If the slope is positive, that means the data is moving up. If the slope is negative, that means the data is moving down. Okay, the slope was positive. So that verifies that R is positive as well. Linear, relationship, association, correlation, however you want to say it. Okay. We probably should say between. It says in context, so we should say between hand spans of left and right. Hand spans of left and right. There should be. I don't know too many people who have one hand that's a lot bigger than the other hand, right? Most of the people have hands that are very, very similar. Nothing's the same. Nothing is the same. But most people have one hand that matches the other, right? That's what it's saying. I can predict one hand very strongly. If you tell me your left hand size, I can predict what your right hand size is going to be pretty strongly. I should be able to, right? Okay. R squared, and then S. So R squared. Okay. So for R squared, we have the number 90.2%. So we're going to use this sentence frame over here. Right here, the explanatory variable. So we're going to change out the word. We're going to change out the word right here. Instead of saying explanatory variable, we're going to say what ours is. And then we're going to change out the percent. And then we're going to change out the response variable. So for ours, I think it said right hand span is X, left is Y. So we would say the right hand span is blank percent responsible for the left hand span. Okay, you would just fill it in. Literally, you just, oops, let me highlight, let me underbox it. That one, and that guy are the ones that you change. Okay. So the reason I can predict your hand span is based on your other hand span. 90% of the reason I can predict it is because of the other guy. Well, that makes sense, right? If you tell me what one hand size is, I'm going to be pretty close to what your other hand is, because most people's hands are very, very similar, very, very close in size. Okay. So let's see, the explanatory variable. The right hand span is 90.2% responsible for left hand span. Okay. Last thing, standard deviation. Sometimes it's called S sub E, sometimes it's just called S. They're both the same thing. Okay. So this number here, this 0.6386. We have a sentence frame for that. This chapter is big on sentence frames because there's a lot of stuff you have to interpret. That's why I put sentence frames in here. Okay. So right here in yellow, we would say on average, each of the points is blank units away from the regression line. On average, each of the points is blank away from the regression line. We would just say units because I think it's inches, but I don't know, maybe centimeters. I don't know what units. They don't say what units they told us. Okay. So on average, each point is blank units away from the regression line. Each point is 0.6386 units away from the regression line, the predicted line. Okay. Even though that number is small, it's kind of crazy. If you guys came in here and said, if I said, okay, I want you to do two things. I have on your desk, you have a ruler. I want you to measure the hand span of your left. And then I want you to do the same thing for your right. You'd be like, why am I doing it twice? It's going to be the same size. But according to this data, they're a little off. They're a little off. Okay? They're not exactly the same. Otherwise, R would have been 1, perfect. If they were exactly the same for everybody, they would have been 1. Now that's pretty close to 1. That's pretty close to 1, but still is a little bit off. It's a little bit off. Okay. All right. So that's, yeah, like I said, that is computer printout. That's how you read that. Okay. So what I want you to do now, the last 25, 30 minutes or so, I want you to start on